In this series of three-dimensional geometry, today we are going to discuss plane. Plane is any surface in which if we take any 2 points, then the line joining these 2 points entirely lies within that surface. Such surface is called a plane. Consider point A whose position vector is a bar on this plane, and let n bar be a normal vector to this plane. Let P be another point on this plane whose position vector is r bar. Then vector AP bar will be perpendicular to this normal vector n bar. Therefore, dot product of AP bar and n bar will be 0 because they are perpendicular vectors. Now AP bar is r bar, which is the position vector of P, minus a bar, which is the position vector of A, dot n bar equals 0. So that will be r bar dot n bar minus a bar dot n bar equals 0. That gives r bar dot n bar equals a bar dot n bar. So this is equation of this plane passing through point A bar and perpendicular to vector n bar. This equation is also known as vector equation of this plane in scalar product form. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. Consider a plane at perpendicular distance d from the origin, so that vector on bar will be equal to d n cap, where n cap is unit vector in the direction of on bar. Consider r bar to be the position vector of any point p x, y, z on this plane, so that op bar equals r bar. Now np bar dot on bar will be 0 because they are perpendicular vectors. So we write r bar position vector of point P minus dn bar position vector of point N dot dn cap position vector of on bar will be equal to 0. Since distance d is non-zero, we write r bar minus dn cap into n cap equals 0. That will be r bar dot n cap minus d n cap dot n cap equals 0. That will be r bar n cap minus d equals 0 because n cap dot n cap is 1. Therefore, r bar n cap will be d, and this is known as vector equation of this plane in the normal form. Further, if L, M and N are the direction cosines or DCs of the unit vector n cap, then from r bar dot n cap equals, we write x I cap plus y j cap plus z k cap for this r, because the coordinates of P are x, y, z dot l I cap plus m j cap plus n k cap for this n cap equals d. Now by the rule of dot product, we get this lx plus this my plus this nz equals d, which is known as Cartesian equation of this plane in normal form. Cartesian equation of a plane can also be found out as follows. Suppose on this plane there is point A, x1, y1, z1, and the direction ratios of the normal vector are a, b, c. If p x, y, z is any point on this plane, then direction ratios of AP will be x minus x1, y minus y1 and z minus z1. Since AP bar is perpendicular to normal vector n bar, therefore AP bar dot n bar will be 0. Therefore, we write equation of this plane as this a multiplied by x minus x1 plus this b multiplied by y minus y1 plus this c multiplied by this z minus z1 equals 0, which also can be written as ax plus by plus cz plus t equals 0. Let's find equation of this plane which passes through point A, whose position vector a bar is 2 I cap plus 3 j cap plus 4 k cap, and which is perpendicular to this vector n bar 2 I cap plus j cap minus 2. We know the vector equation of a plane which passes through point A with position vector a bar and normal to vector n bar is r bar dot n bar is equal to a bar dot n bar, where this a bar dot n bar is distance d of the plane from origin. So r bar n bar will be a bar, which is 2 I cap plus 3 j cap plus 4 k cap dot n bar, which is 2 I cap plus j cap minus 2 k cap. So that will be 2 multiplied by 2 plus 3 multiplied by 1 plus 4 multiplied by minus 2. That will be 4 plus 3 minus 8. So we get r bar dot n bar equals minus 1. So vector equation of this plane will be r bar dot 2 I cap plus j cap minus 2 k cap equals minus 1, where r bar is position vector of any point p x comma y comma z on this plane. Let us see how to find Cartesian equation of this plane which passes through point A 1, 2, 3, and direction ratios of the normal n to this plane are 3, 2, 5. If coordinates of A are x1, y1, z1, and the direction ratios of this normal are a, b, and c, then Cartesian equation of this plane will be a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. So we get 3 into x minus 1 plus 2 into y minus 2 plus 5 into z minus 3 equals 0. That will be 3x plus this 2y plus this 5z minus 3 minus 4 minus 15 equals 0. That will be 3x plus 2y plus 5z minus 22 equals 0. So this will be the Cartesian equation of this plane. In this figure, OM is perpendicular to this plane, and the coordinates of the foot of this perpendicular M are 2, 1, minus 2. From this information, we have to find vector equation of this plane. Since OM bar is perpendicular to this plane, therefore drs of OM bar will be 2, 1, and minus 2. Now point M is on this plane, which means that the plane passes through M, whose position vector will be 2 I cap plus j cap minus 2 k cap. Therefore, we have drs A equals 2, B equals 1, and C equals minus 2, and A bar equals this vector. So the vector equation of the plane will be r bar dot n bar equals a bar dot n bar. So therefore it will be r bar dot n bar, which is 2 I cap plus j cap minus 2 k cap equals 2 I cap plus j cap minus 2 k cap multiplied by n bar, which is also 2 I cap plus j cap minus 2 k cap. This will be 2 multiplied by 2, 4, plus 1 multiplied by 1, 1 plus minus 2 multiplied by minus 2, 4. That will be 9. So the vector equation of this plane will be r bar dot 2 I cap plus j cap minus 2 k cap equals this 9. Now we will see vector equation of a plane which passes through a point A on the plane whose position vector is A bar and it is parallel to vectors B bar and C bar, which can be considered to lie in the same plane. Now we know that B bar cross C bar will be perpendicular to the plane containing B bar and C bar. So therefore this B bar cross C bar is nothing but the normal vector n bar which we have already referred to. Now we have familiar situation of a plane which passes through a point A whose position vector is A bar and n bar is a normal vector of this plane. So the vector equation of this plane will be AP bar dot normal vector n bar equals 0, where P x comma y comma z is any point on this plane whose position vector is r bar. So therefore we write vector AP bar as r bar, which is the position vector of point P, minus A bar, which is the position vector of point A, dot B bar cross C bar, normal vector represented by n bar equals 0. Now this will be r bar dot B bar cross C bar, and because of this minus sign it will be A bar dot B bar cross C bar, which is the required vector equation of this plane. Here we can note that if AP bar, B bar and C bar lie in the same plane, then they will be coplanar vectors and can be written as a linear combination AP bar equals lambda B bar plus mu C bar, where lambda and mu are non-zero scalars. Therefore same equation can be written as r bar minus A bar for this AP bar equals lambda B bar plus mu C bar, or r bar equals A bar plus lambda B bar plus mu C bar. This is called vector equation of a plane in parametric form. We are given vector equation of a plane in parametric form as r bar equals I cap minus j cap plus lambda times I cap plus j cap plus k cap plus mu times I cap minus 2 j cap plus 3 k cap. If we compare this with the standard vector equation of a plane in parametric form given as r bar equals A bar plus lambda B bar plus mu C bar, we will get A bar equals this I cap minus j cap, B bar equals this I cap plus j cap plus k cap, and C bar equals this I cap minus 2 j cap plus 3 k cap. Here vector n bar, which is B bar cross C bar, is perpendicular to this plane. So we first write n bar equals B bar cross C bar, which will be a determinant I cap, j cap, k cap, then this 1, 1, 1, then this 1, minus 2, 3. This will be 3 plus 2, 5 I cap, minus 3 minus 1, 2, j cap, minus 2 minus 1 minus 3. So the direction ratios of this normal will be 5 minus 2 minus 3, and since the plane passes through point A whose coordinates from this vector A bar will be 1 comma minus 1 comma 0, so the Cartesian equation of this plane will be this A into x minus this x1, that is 1, plus this b, that is minus 2, into y minus this minus 1, that is plus 1, plus this c, that is minus 3 into z minus this 0 equals 0, which after simplification will be this 5x minus 2y minus 3z, then minus 5 minus 2 minus 7 equals 0 will be the required Cartesian equation of this plane. Next we will find vector equation of a plane passing through three non-collinear points. We know that there are infinite number of planes passing through 2 points, but there is a unique plane passing through three non-collinear points. So we will consider a plane passing through three non-collinear points A, B and C, whose position vectors are A bar, B bar and C bar respectively, and the vectors passing through them will be AB bar and AC bar. If P is any point on this plane whose position vector is R bar, then we have this vector AP bar. Now vectors AP bar, AB bar and AC bar are coplanar, and we know that box product of three coplanar vectors, which will be AP bar dot AB bar cross AC bar, equals 0. Now for AP bar we write R bar minus A bar dot AB bar cross AC bar equals 0, which further will be R bar minus A bar dot B bar minus A bar for this AB bar cross C bar minus A bar for this AC bar equals 0. So we write the vector equation of this plane passing through three non-collinear points A, B and C in the form of a box product R bar minus A bar, B bar minus A bar, C bar minus A bar equals 0, which is the required equation of this plane. Here we must note that vector AB bar cross AC bar is nothing but the normal vector n bar to this plane that we know of. So the situation here is same as equation of a plane passing through point A bar and normal vector n bar to this plane. Now we will solve a problem based on this. We are given a plane which passes through three non-collinear points A, B and C, whose coordinates are 1, 1, 2, 0, 2, 3 and 4, 5, 6, and we have to find equation of this plane from the coordinates of these points. First we will find out their position vectors. So position vector of point A will be A bar equals I cap plus j cap plus 2k cap. That of B bar is 2j cap plus 3k cap, and that of C is C bar equals 4I cap plus 5j cap plus 6k cap. First we will find a vector normal to this plane. So for that we will find AB bar, which is B bar minus A bar, that is 0 minus 1 minus I cap, 2 minus 1 plus j cap, 3 minus 2 plus k cap, and AC bar, that will be C bar minus A bar, which is 4 minus 0 4 I cap, 5 minus 2 plus 3 j cap, 6 minus 3 plus 3 k cap. Now the vector normal to this plane will be B bar minus A bar cross C bar minus A bar. So let's find out B bar minus A bar cross C bar minus A bar. That will be a determinant I, j, k, then this minus 1, 1, 1, then this 4, 3 and 3. That will work out 3 minus 3, 0 I cap. So that will be 0 minus of minus 3 minus 4 j cap plus minus 3 minus 4 k cap. So that will be 7 j cap minus 7 k cap. So this is our normal vector n bar. Now the plane passes through point A, whose position vector is I plus j plus 2k, and A vector normal to this plane is n bar, which is 7j minus 7k. So from these two things we write equation of the plane for any point P x comma y comma z on this plane whose position vector is r bar. We write equation of this plane as r bar minus a bar dot the normal vector 7j cap minus 7k cap equals 0. That will be r bar minus a bar, which is I cap plus j cap plus 2k cap dot 7j cap minus 7k cap equals 0. So that will be r bar dot 7j cap minus 7k cap, because of this minus sign, equals I cap plus j cap plus 2k cap dot 7j cap minus 7k cap. That will be r bar dot 7j cap minus 7k cap equals, the dot product will be 1 multiplied by 0 plus 1 multiplied by 7, that is 7, 2 multiplied by minus 7 minus 14, so that will be minus 7. So our required equation will be r bar dot 7j cap minus 7k cap equals minus 7. We will see what will be the normal form of a plane. We have this plane perpendicular to the vector ON, whose magnitude or length is P, and the unit vector along this perpendicular is n cap. So we write vector ON bar equals P n cap. Let P be any point on this plane whose position vector is r bar, and we can see that vector np bar is perpendicular to this unit vector n cap, which follows that np bar dot n cap will be 0, that is r bar, which is position vector of p, minus on bar position vector of n dot n cap equals 0. So that will be r bar minus p n cap dot n cap equals 0. That will be r bar dot n cap minus p times n cap dot n cap equals 0. That will be r bar dot n cap minus n cap dot n cap will be 1. So this will be p equals 0. So finally we get r bar dot n cap equals p is the equation of this plane in the normal form. It is also known as normal form of vector equation of a plane. Now we will see normal form of the Cartesian equation. In this figure, if L, M, N are direction cosines of this normal to this plane, then we have the unit vector n cap in the direction of this normal as L I cap plus M j cap plus N k cap. If distance of this plane from origin, that is length ON, is P, then coordinates of n will be PL, PM, PN. Then equation of the plane will be Lx plus My plus Nz equals P, which is known as normal form of the Cartesian equation. There are two planes at a distance P from the origin, and they will have n cap as the unit vector in the direction of the normal, and those two equations will be r bar dot n cap equals plus minus p. With plus p, it will be the equation of this plane, and with minus, it will be the equation of this plane on the opposite side. We have to find equation of this plane. The plane is at a distance of 6 units from the origin, and a normal vector n bar to this plane is given as n bar equals 2 I cap minus j cap plus 2 k cap. We have to find vector equation of this plane. First we find magnitude of normal vector n bar, that will be square root of this 2 square 4 plus this minus 1 square 1 plus this 2 square 4, that will be square root of 9 or 3. So the unit vector n cap in the direction of this ON bar will be vector n bar upon its magnitude mod n bar. So that will be 1 upon 3 2 I cap minus j cap plus 2 k cap. Now for any point P whose position vector is r bar, vector equation of the plane will be r bar dot n cap equals P, where P is distance of the plane from the origin, which is given to be 6 units. So we write r bar dot n cap, which is 1/3 of 2 I cap minus j cap plus 2 k cap equals 6. That will be r bar dot 2 I cap minus j cap plus 2 k cap equals 3 6 are 18. So this is the required vector equation of this plane. We have to find the perpendicular distance of this plane from the origin, whose equation is x minus 3y plus 4z minus 6 equals 0. Now in order to find the distance P, we first write this Cartesian equation of the plane in the normal form: Lx plus my plus nz equals P. From the equation of the plane, we can find direction ratios of the normal to this plane, which will be this 1 minus 3 4, then square root of this 1 square plus this minus 3 square plus this 4 square will be square root of 26. So the dices of the normal n bar will be this 1 upon root 26, this minus 3 upon root 26, this 4 upon root 26. This normal equation can be written as 1 upon root 26x minus 3 upon root 26y plus 4 upon root 26z equals, from this it will be 6 upon root 26. Comparing these two equations, the distance of this plane from origin, that is P, will be 6 upon root 26. We have to find the coordinates of the foot of the perpendicular n, where the equation of this plane is 2x plus y minus 2z equals 18. We have the perpendicular distance ON equals P. Now we know that if L, M, N are the direction cosines of the normal to this plane, and P is the perpendicular distance of this plane from origin, then the coordinates of the foot of the perpendicular n will be LP, MP, NP. So we need to find the direction cosines. Now first we will write the direction ratios of the normal from the equation of the plane, which will be 2, 1, minus 2. Square root of this 2 square plus this 1 square plus this minus 2 square will be square root of 9, that is 3. So the DCs of the normal will be this 2 upon 3, 1 upon 3 and minus 2 upon 3. So the normal form of the equation of this plane will be this 2 upon 3 x plus 1 upon 3 y minus 2 upon 3 z equals, from this Cartesian equation, 18 upon this 3, that is 6. Comparing this equation with Lx plus my plus nz equals P, we get the perpendicular distance P equals 6. Now we will write the coordinates of the foot of the perpendicular n as LP, that is this 2 upon 3 into 6, MP, that is this 1 upon 3 into P, which is 6, comma this minus 2 upon 3 into this P. So that will be 3 2s are 3 2s are 3 2s are, which will be 4 comma 2 comma minus 4. So these are the coordinates of the foot of the perpendicular n to this plane. We have to convert equation of plane r bar dot 3 I cap minus 4 j cap plus 12 k cap equals 8 to normal form and find perpendicular distance of the plane from the origin O and direction cosines of the normal to this plane. From this given equation, we have n bar equals this 3 I cap minus 4 j cap plus 12 k cap. So its magnitude mod n bar will be square root of this 3 square 9 plus minus 4 square 16 plus 12 square 144. That will be square root 169, which will be 13. So unit vector in the direction of normal vector n cap will be n bar upon its magnitude mod n bar. That will be 1 upon 13 times 3 I cap minus 4 j cap plus 12 k cap. Now the normal form of the plane will be r bar dot n cap equals p. That will be r bar dot 3 I cap minus 4 j cap plus 12 k cap upon this 13 equals this 8 upon this 13. Now perpendicular distance of the plane from the origin O will be this 8 upon 13, and direction cosines of the normal to the plane will be this 3 upon 13 minus 4 upon 13 and this 12 upon 13. If you like this video, please share this to your classmates. Don't forget to subscribe this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.